What we want to talk about is this, the inverse of a function. Underline that word. This is both really basic and, Rachel, hugely profound. What is the inverse? The inverse is the undoing or opposite operation. What I used to teach my kids is if you plug in a number and get an answer, the inverse function lets you plug in the answer and gives you the original number back. You've been doing inverses all your life without realizing it. What's the inverse of plus 5 minus 5? What's the inverse of squaring? Physics 12 is how do you get rid of squared. Really what I should have said, instead of saying how do you get rid of a squared, what I should have said was what's the inverse of squaring? Apply that function, it'll give you your answer back, your original number back. What's the inverse of minusing 6? What's the inverse of multiplying? Dividing. What's the inverse of sine? That's trickier. Although your calculator does have an inverse button for that reason very often. I think yours is a second function button, but sometimes you'll see it labeled as an inv, short for inverse button. So that's the notion of an inverse. It's the opposite mathematical function, but we're going to formalize it. It says this. Ready? A function or a relation maps each element of set A, which you learned last year and in previous years was the domain. Remember, the domain is what we think of as the x values. To the elements of a set B, the range, or what we think of as the y values. So here is a diagram that shows the function is half of, is 0.5 of. Ready? 1 is half of 2. Yes? 3 is half of 6. 4 is half of 8. 2 is half of 4. We would say the domain is the set 1, 2, 3, 4. We would say the range is the set 2, 4, 6, 8. It says complete the following. If you were to graph this graph goes through 1, 2, 2, 4, 3, 6. What's the last point that we're missing? 4, 8. The inverse of a function or a relation undoes what the function or relation did in the first place. Really, here's what it, if I want to get technical, Ashley, here's what it says. If I have a set A and you have some kind of operation that maps it to B, the inverse will map everything from B back onto A. A 2 will turn into a 1. A 6 will turn into a 3. A 8 will turn into a 4 in this particular example. The inverse of is half of would be the function called is twice or is double of. With the domain 2, 4, 6, 8. 2 is the double of 1. 4 is twice as big as is the double of 2. 8 is twice as big as is the double of 4. What would the points on the inverse be? 2, 1. 4, 2. Right? 6, 3. And I'm running out of room. 8, 4, and I'll do my squiggly bracket there just so I can write bigger. By the way, this is important. Logan, if you're paying particular attention, you may have noticed that the domain of my original ends up as the y values, as the range of my inverse. And the range of my original, the y values, ends up as the domain of my inverse. What I've really just done is cut the amount of graphs you have to memorize in half. One of the skills I'm going to try and teach you in this unit is this. Mackenzie, if you know an original graph, you know how to graph its inverse. Don't memorize that. Its domain is going to become its range. Its range is going to become its domain. And actually, it's going to be even more specific than that. Okay? In grade 12, in the old Math 12 course, and in the current pre-calc course, there's a whole unit on transformations, on graphing. And I would always tell my kids, Mark, I can cut your memorization in half. Don't memorize this. We'll memorize its inverse. We can find the original one easily. Or, don't memorize this. It's the inverse of one you already know. It says, plot the points representing the function on the grid. So I'm going to change colors because I can. I'm going to plot the original function in blue. And the original function went through 1, 2, 2, 4, 3, 6, and 4, 8. I'm going to graph the inverse in red. The inverse didn't go through 1, 2. It went from 2 through 2 over, 1 up. The inverse didn't go through 2, 4. It went through 4 over, 2 up. The original did not go through 3, 6. It went through 6 over, 3 up. And the inverse does not go through, I think I said the original, the inverse does not go through 4, 8. The inverse goes through 8, 4. I'm going to connect both of these lines. Here's the blue one. Here's the red one. And if you turn your heads kind of 45 degrees, tilt your heads, you might notice that it looks like if I creased this piece of paper right along that line there, these would fold on top of each other. And that's also going to be a very profound shortcut. We call that a reflection line. Okay? It says this, the fourth part, Brianna says, draw a mirror line which represents the axis of symmetry of the graphs. Say what? Draw a line that goes through 0, 0, you know what, I'm going to do it in green. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, negative 1, negative 1, negative 2. If you do a dotted line like this, and you tilt your head like Rachel already is, 45 degrees. Yeah. Fancy word. We say this is a reflection. Brendan, we call it a reflection. Write that. You guys with me?
Yeah.
Call it a reflection. Now, this line that goes through 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 1.1, 1.1, 2.63, comma 2.63, negative 19.2, comma negative 19.2, has a special equation. We say this, it's a reflection about y equals x. Any inverse graphs, if you see them on the same grid, you'll notice they're reflections about the line y equals x. They're reflections about 1, 1, 2, 2, 3, 3, 4, 4, 5, which really means this. If you graph the original, Mackenzie, you can graph the inverse by reflecting it without actually doing any of the math. You can graph it graphically, which sounds strange because I had graph. You could graph it artistically, whatever. You can draw it. Okay? You don't realize how profound that is yet. Next page. consider the table shown for the original function and its inverse. So here's the function, that's the first horizontal line, and then beneath it is the inverse. And I've given you the function several different ways. In words, I've given it to you as coordinates. Those are not my favorite. To me, Rachel, my favorite is as an equation because that's the least amount of writing. And I can give you the domain and the range. Okay? So, is half of, Mr. Dueck, you said is half of, why isn't there a 0.5 in the equation? Here's what we're saying. If you take the x and double it, you'll get the y value because the x is half as big as it needs to be. You better multiply it by 2 to get the y value. That's what will give you, put a 1 in, get a 2, put a 2 in, get a 4, put a 3 in, get a 6, put a 4 in, get an 8. This is my original function. What would the inverse equation be? How do you find an inverse? Well, it turns out to find an inverse, we switch the x and y around, which sounds very strange, but here is how you find an inverse equation. Brianna, my joy, can you read to me the original equation? Look up right here. The inverse is going to be, switch the x, wherever there's an x, write a y. Wherever there's a y, write an x. And then get the y by itself, because that's how we write equations. How would I get the y by itself here? All my physics kids are like, really? Yeah, Grayson, you're right. Divide by 2. Y equals what? X over 2. That is the inverse equation. Switch the x and y around, and then, Brandon, get the y by itself. That'll give you your inverse equation. And what do I mean by an inverse equation? In this equation, if I plug in an x, I'll get an answer. In this equation, if I plug in the answer, I'll get my original x back. Brendan, give me a number between 50 and 100. 2 times 74 is 148. 148 divided by 2, 74. That's the inverse equation. And we're starting off with one that hopefully is fairly intuitive, but I'm telling you, that'll work for a far more complicated equation with squareds and logs and roots and whatever. If you switch the x and y around and get the y by itself, that's the inverse equation. It's just more work is all. So we wrote here the equation of the function originally was y equals 2x. Interchange x and y to get the equation of the inverse, and then get the y by itself. There's step 1, there's step 2. Here's the function. This is the relation, is the square root of. Negative 2 is the square root of 4. Positive 2 is also the square root of 4, because if you square negative 2, you'll get 4. If you square positive 2, you'll get 4. Negative 3 and 3 are the square roots of 9, because negative 3 squared is 9 and positive 3 squared is 9. Here's my domain. Here's my range. If I wanted to find the inverse, what I'm looking for is something that will start with a 4 and map to a negative 2 or a positive 2, and start with a 9 and map to a negative 3 or a positive 3. Okay? And it says complete the chart. In English is the square root of, here's what I'm really talking about. The points are negative 2, 4, positive 2, comma 4. Negative 3, comma 9, positive 3, comma 9. The domain is negative 2, 2, negative 3, 3, although you could write that in order and go from negative 3 to 2, but whatever. The range is 4 and 9. The equation, I think it's this, y equals x squared, because I'm pretty sure negative 2 squared is positive 4, 2 squared is 4. Negative 3 squared, positive 9, 3 squared, positive 9. So here's the question I'm asking. What is the inverse of that equation? Now, in physics, I have often said, well, how do I get rid of a squared? And what have people said? Which is technically wrong. Right in physics, wrong in math. Say what? Well, yeah, because here's what I need. I need to get back 4 comma negative 2 and 4 comma 2. I need to be able to flip my x and y's around as points or as an equation or as a graph. I need to be able to get back, instead of negative 3 comma 9, I want 9 comma negative 3 and 9 comma positive 3. The only way I can do this starts with physics. How to get rid of a squared? What's the inverse of squaring? Square rooting is technically wrong, but what is correct, Jake, is this: plus or minus the square root of x. That gives you your positive or your negative answer. Because square root, Logan, is defined as the positive answer. For me to get that negative answer. Now, ready? I told you you could find the inverse. How? By switching. So you got some room at the bottom of the page. Here is the inverse. I start with this equation. Wherever there's an x, I write what? A y. Wherever there's a y, Darian, I write. So you ready? The inverse equation would start like this: x equals y squared. And then you would say to yourself, how to get rid of a squared? But you learned, hopefully last year, maybe you didn't, you should have learned that when you square root an equation, this is not in physics, because in physics it's often time that we're square rooting and we don't want a negative time, we don't care about a negative time. But in math, Logan, whenever you square root an equation, see, this is a quadratic, there should be 2 answers. It's going to be plus or minus the square root of x equals y. That's why that has to occur. This is going to give you a range of 4 and 9 and a domain of negative 2 and 2 and negative 3 and 3. Ready, Carson? How do you find an inverse? Switch the x and y around. When you do that, your domain of the original becomes the... Of course it should, because if domain was the x's, those should become the y's of my new one, because you've just told me, how do I find an inverse? Switch the... Well, why shouldn't all my x and y related stuff switch? They do. Okay? Oh, and the range of my original becomes the... of the inverse, domain of the inverse. Which, by the way, also cuts down on your memorizing. Here's what it means. Any function that you already know how to graph and that you know the domain and the range of, you also know the domain and range of the inverse. If I gave you, you guys did the parabola a whole bunch last year. If I gave you a graph and I told you it was an inverse of a parabola, if you knew what parabola it came from, you could tell me its domain and range of the inverse. Because the domain of the original parabola would be the range, and the range of the original parabola would be the domain. Oh, and it would look like a reflection about the line y equals x. Turn the page. It says, plot the points representing the original relation on the grid. Now, the original relation was when x is 2, we're 4 up. When x is negative 2, we're 4 up. When x is 3, we're 9 up. When x is negative 3, we're 9 up. Right? This one, I'm not going to connect. By the way, can you see it's sort of based on a parabola? I'm not going to connect it, though. Then, it says, plot the points representing the inverse. Now, what was the inverse? Oh, by the way, I'll again go blue for the original, and I'll do the inverse in red just so you can see the difference. You gonna make it, Pam? Okay. Ah! No? Nothing? What were the points on the inverse? 4 comma negative 2 and 4 comma positive 2. 4 over negative 2, 4 over positive 2. 3 over negative 9, 9 over negative 3, and 9 over positive 3. 9 over negative 3, 9 over positive 3. If I just connect these two, yoink, and connect those two, yoink, and if I go to my original, connect those, because that's part of the parabola, that's part of the parabola. Again, if I sketch in that line y equals x that goes through 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, if I sketch in this line here, are they mirror images, fancy word, reflections of each other about the line y equals x? Yep. Yep. Okay. So part 3 said join the points together. We did that. Part 4 said draw a mirror line. That's that dotted line that I've drawn in there. What is the equation of that line? Carson, how did I find an inverse? Switch the... I'm going to say that a different way. You know how you find an inverse? Let the y equal x and the x equal y. Oh, it's not a coincidence that that's what it ends up reflecting about, because that's the line where y equals x and x equals y. Now I actually say, yeah, it kind of makes sense. I didn't predict it, but in hindsight, sure, sure. In fact, any point on this line is its own inverse. What's the inverse of 1, comma 1? 1, comma 1. I switched the x and y around. Did you see it? What's the inverse of negative 2, comma negative 2? Negative 2, comma negative 2. I did switch the x and y around. It's just the same thing. Okay? Put your pencils down, look up. The problem here is, I saw Kyle going to his graphing calculator. If you're planning on graphing this, we have a problem. We have a problem with the red graph. Do you remember way back in Math 10? Remember, you're all shorter, younger, some of you. You had something called, if you had a good Math 10 teacher, he would have drummed this into you, the vertical line test for functions. This red graph fails the vertical line test. If my finger is a vertical line, you can see my finger's shadow touches the graph in more than one location. You know what that means? It means your graphing calculators can't graph it because it's not a function. However, Kyle, I have some pretty impressive software that can. So put your pencils down, look up. By the way, if any of you want a very good free graphing program, it's called WinPlot. This guy knows how to code. He's from a university. He just made it as a labor of love. It looks like almost nothing. It is one of the most powerful graphing programs I've ever seen. So the first equation is the parabola y equals x squared. I'm going to make the line a little thicker. Looks like that. You've seen that one a whole bunch. This second, how do I find an inverse? Turns out on this software, I graph what's called an implicit equation, which means I'm going to go, what did you say? Switch to x equals y squared. There. Okay? Now, I'll add the line y equals x, which we think it's a reflection about. Is it a reflection about the line y equals x? Yep. Yep. That's how I know it's an inverse. Its domain became its range, and its range became your domain. By the way, the red graph, which is the parabola, what was the domain of every parabola? How far left, how far right? Infinity. What was the range of this particular parabola? Everything above and touching 0. Let's write that in our notes. Our particular parabola, the domain, remember you wrote it like this, x, e, r, that was all reals. And the range y above and touching 0. Carson, how do I find an inverse? Say it again, what? So if I hear you correctly, in theory, without actually graphing, I should be able to say the domain is everything to the right of 0. And I should find that the range, because I'm putting an x, I'm putting a y where the x was, the range should be all reals. That should be the case if our method works. Hey, let's look at this blue graph. Is it everything to the right and touching 0? Yep. And does it go all the way up forever? And does it go all the way down forever? Does it have a range of all reals? So I've got a shortcut method, Logan, where if my graphing software can't handle something, my brain can pretty easily. The domain becomes the range of an inverse, and the range of the original becomes the domain of the inverse. Or, my shorthand version, Julia, switch the x and y's. So if I give it to you as a set of ordered pairs, then Mark, literally switch the x's and y's. As an example, if the original goes through 1, 9, what does the inverse go through? 9, 1. That easy. Don't waste your time. If I give it to you as an equation, you have to do some algebra. Wherever there's an x in the original, put a y. Wherever there's a y in the original, put an x, and then get the y by itself. That's your inverse equation. Or, if I give it to you as a graph, it's a reflection about the line y equals x. I'll be honest, I don't use that method. If it's a graph and the graph goes through 5, 6, what will the inverse go through? If the graph goes through 5, 6, what will the inverse go through? 6, I don't actually reflect it. I just know, oh, 5, 6 becomes 6, 5. 2, -8 becomes -8, 2. That's why you heard me calling the points out when I was doing this one by hand. And then afterwards I say, oh yeah, it's a reflection. I find the actual reflecting thing tricky, but I can switch x and y around by hand really easy. Oh, and then key idea again. The domain of the inverse is the range of the original. The range of the inverse is the domain of the original. Okay? You do not yet realize how profound this is. But what this is going to allow us to do is to define a function that we know and then make up a brand new function that we know must be its inverse. We're going to say, here's the property it has to have. It has to switch the x and y around. Its domain has to be the range of my original. Its range has to be the domain of my original. And we're going to give that function a brand new name, and we're going to find a brand new button on our calculator that does it. Example 4 says, determine the inverse of a function defined by that equation. Oh, how do I find the inverse of an equation? Carson. So I would start out by going like this. X equals 5y minus 6. But I wouldn't stop there because my calculator can't graph that. The next step is get the y by itself. How would I get the y by itself? What would I do first? Add 6. So this is the same as x plus 6 equals 5y. You okay, Mackenzie? I did it in my head, not showing any steps. I haven't quite got the y by itself. Mackenzie, what else is next to the y? I think you're right, but I couldn't hear a word you said. The 5, what's the 5 doing to the y? Adding, subtracting, multiplying, or dividing? So how, multiplying? Oh, what's the inverse of timesing by 5? Dividing by? So now I can say it properly. By the way, up until last year, I said, what's the opposite? Really, I should have said, what's the inverse? So, Mackenzie, if I hear you correctly, you're saying x plus 6 all divided by 5. Now, if you're right, it means any number that I plug in here and get an answer for, if I plug the answer in, I'll get the number back. Pick a number between 1 and 10, Mackenzie. 7. Nice peer pressure. Ready? Mackenzie, what's 5 times 7? 35 minus 6, 29. So 7 gives me 29. That means if I put a 29 in here, I should get a 7. What's 29 plus 6? Divided by 5? 7. Works. Works. That's one of my built-in error checks, especially if it's a very complicated equation and I'm not sure if I did it right. I'll plug in a couple of numbers into my original, get answers. I'll plug the answers into my inverse. I better get the original numbers back. If I don't, I've goofed. What's your homework? If you haven't finished 1, 2, and 3, finish 1, 2, and 3. You can do number 4. Number 5. Now, number 6, I'm going to write this. G period C period. What does G period C period stand for? Graph these on your graphing calculator. Now, if you were here last class, I told you how to set up your view window to go between -10 and 10. See, I was thinking of this. And -10 and 10. See if you can figure out how to type that in. Then, find some points on here. Once you've done that, to find the inverse, just switch your x's and y's around. In other words, if this goes through, and I'm making this up, 7, 9, your inverse will go through 9, 7. Okay? Graphing calculator for this as well. You're going to have to kind of muck around with your calculators, and this is me letting you work with it. Number 7 is good. Number 8 is good. So far I've assigned everything. Yeah, I know. Number 9 is good. Number 10 is good. Okay? You got lots of time to get all this done and any other missing assignments that you want to show me from the last unit.